Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. A symphony of radio waves. Unveiling the invisible universe. Humanity has always gazed at the night sky, marveling at the twinkling tapestry of stars and the occasional streak of a comet. Our traditional view of the cosmos has been shaped by what our eyes can perceive, the visible light spectrum. However, this is just a sliver of the story. Beyond the realm of visible light lies a hidden symphony, a universe teeming with activity that plays out in a different register, the realm of radio waves. Radio astronomy, a relatively young branch of astronomy compared to its optical counterpart, unlocks this hidden dimension. By harnessing the power of radio waves, astronomers can peer through thick dust clouds that obscure our view in the visible spectrum. This allows them to observe objects that would otherwise remain invisible, unveiling a universe brimming with wonders that were previously beyond our reach. Imagine a vast celestial orchestra, where stars, galaxies, and even the faint afterglow of the Big Bang itself all contribute to a symphony of radio waves. Radio astronomy grants us access to this cosmic concert, allowing us to not only appreciate the beauty of the celestial light show, but also to understand the underlying processes and mechanisms that govern the universe's grand performance. The messengers, radio telescopes, giants with ears. Unlike their optical counterparts, the majestic telescopes with gleaming domes that gather visible light, radio telescopes operate on a completely different principle. Instead of capturing fleeting photons of light, they act as colossal radio antennas, designed to collect the faint radio waves emitted by celestial objects. These radio telescopes come in a variety of shapes and sizes, each with its own strengths and specialties. Some resemble giant dish antennas, like the iconic Arecibo Observatory in Puerto Rico, with a massive dish that can be pointed towards specific regions of the sky. Others, like the Very Large Array in New Mexico, consist of numerous smaller antennas spread out over vast distances, working together as a single, powerful instrument. The design of a radio telescope is crucial for its effectiveness. The size of the dish or the spacing between antennas in an array determines the telescope's ability to resolve fine details in the radio sky. Just as a larger radio antenna on your home stereo provides better reception, a larger radio telescope can pick up fainter signals and distinguish between objects that are close together in the sky. Despite their outward differences, all radio telescopes share a common goal: to capture the faint whispers of the cosmos in the form of radio waves. These telescopes act as our ears to the universe, allowing us to listen in on the celestial symphony and interpret the hidden messages carried by these radio waves. Tuning in. How radio telescopes work. Imagine a radio receiver carefully tuned to a specific station on the dial, filtering out the background static to bring in a clear signal. Radio telescopes employ a similar strategy, but instead of your favorite music station, they're focused on the faint whispers of the cosmos emanating from distant celestial objects. These telescopes can be precisely steered, much like a satellite dish aligning with a specific TV satellite. By meticulously pointing the telescope towards a particular region of the sky, astronomers can target objects of interest for in-depth observation. Once a target is locked, the real magic begins. The radio telescope's receivers act as sophisticated cosmic translators, transforming the faint radio signals into a language we can understand. These receivers are tuned to specific radio frequencies expected to be emitted by the target object. Every celestial object, from swirling nebulae to colossal galaxies, possesses a unique radio signature, a specific range of radio waves dependent on its composition, temperature, and even motion. By meticulously analyzing the strength and characteristics of these radio waves, astronomers can unlock a treasure trove of information about the object under study. A celestial zoo, unveiling diverse astronomical objects with radio waves. Radio astronomy paints a vibrant picture of the universe, revealing a menagerie of celestial objects that remain invisible to optical telescopes. Unlike visible light, which can be easily blocked by dust and gas, radio waves pass through these interstellar clouds with minimal interference. This allows us to peer into the hearts of nebulae, witness the birth of stars in their cradles, and even detect the faint echoes of the Big Bang itself. Nebulae. These vast clouds of gas and dust are the nurseries of stars. However, the early stages of star formation are often shrouded in thick dust, making them invisible to optical telescopes. Radio waves, however, can penetrate this dusty veil, revealing the intricate filaments of gas and the dense clumps where new stars are taking shape. Interstellar medium. The space between stars is not truly empty. It's filled with a sparse but vast reservoir of gas and dust, the interstellar medium. Radio astronomy allows us to study the composition and motion of the interstellar medium, revealing the raw materials from which stars and planets are born, and providing insights into the large-scale structure of galaxies. Pulsars and neutron stars. These incredibly dense remnants of massive stars are invisible at optical wavelengths. However, pulsars, rapidly spinning neutron stars, emit powerful beams of radio waves that sweep across the sky like a cosmic lighthouse. Radio telescopes can detect these pulsating signals, allowing us to study the properties of neutron stars and their interactions with their surroundings. Black holes. These enigmatic objects with immense gravity gobble up everything that ventures too close, including light. However, the swirling matter around a black hole can emit radio waves, providing indirect clues about the presence and behavior of these invisible giants. Unveiling the Galactic Cradle, Radio Astronomy and Star Formation. The birth of stars is a dramatic and complex process shrouded in dust and gas. However, radio astronomy acts as a powerful tool for peering into these stellar nurseries. By studying the radio emissions from interstellar clouds, astronomers can trace the journey of star formation, from the initial collapse of the cloud due to gravity to the ignition of nuclear fusion within the newborn star. Molecular clouds. These cold, dense regions of the interstellar medium are the prime locations for star formation. Radio telescopes can detect specific molecules like ammonia or water vapor within these clouds, acting as tracers for the presence of dense gas and potential star-forming regions. Masers. These natural amplifiers of radio waves, akin to lasers but for radio frequencies, can be found within star-forming regions. By studying maser emissions, astronomers can measure the velocities of gas within the cloud, providing insights into the dynamics of collapse and the formation of protostellar disks, the swirling circumstellar disks that give birth to planets. HII regions. Once a massive star ignites, it emits intense radiation that ionizes the surrounding gas, creating a glowing bubble known as an HII region. Radio observations of these regions reveal the presence of young stars, allowing astronomers to map the recent star formation history within a galaxy. Mapping the Milky Way. Unveiling our galactic structure. Our home galaxy, the Milky Way, is a vast spiral galaxy filled with billions of stars, dust, and gas. However, much of the central region is obscured by thick dust clouds, making it impossible to study its structure with optical telescopes alone. Radio astronomy offers a unique perspective, allowing us to peer through the dust and map the Milky Way's grand design. Spiral arms. The Milky Way is a barred spiral galaxy with prominent spiral arms where most star formation occurs. Radio observations of the distribution of neutral hydrogen gas, a key component of the interstellar medium, trace the structure of these spiral arms, revealing the distribution of gas and ongoing star formation throughout the galaxy. Supermassive black hole. At the very center of the Milky Way lies a supermassive black hole, Sagittarius A star. While we cannot directly observe the black hole itself, radio telescopes can detect the faint radio emissions from the swirling gas and dust around it, providing indirect evidence of its presence and allowing astronomers to study its properties. Stellar populations. Different regions of the Milky Way harbor stars of varying ages and compositions. Radio astronomy allows us to study the distribution of different stellar populations, revealing the galaxy's evolutionary history and the processes that shaped its current structure. Beyond our galaxy. Unveiling distant galaxies with radio waves. the vast expanse of the universe holds countless galaxies beyond our own Milky Way. Studying these distant galaxies with optical telescopes presents challenges due to their immense distances and the dimming effect of cosmic expansion. However, radio astronomy offers a powerful tool for peering into the depths of the cosmos and unveiling the secrets of these faraway galaxies. Redshift in distance. Light emitted by distant galaxies undergoes a phenomenon known as redshift. As these galaxies recede from us due to the expansion of the universe, their light waves are stretched, shifting towards the red end of the spectrum. While this makes them fainter and redder in the visible spectrum, radio waves are less affected by redshift, allowing us to detect them even from incredibly distant galaxies. Early universe. Radio telescopes can detect faint radio signals from some of the most distant galaxies, providing a glimpse into the early universe. These galaxies, formed billions of years ago, can be studied to understand the processes of galaxy formation and evolution in the young universe. Active galaxies. Some galaxies harbor supermassive black holes at their centers that actively accrete surrounding gas and dust. This process releases enormous amounts of energy, often creating powerful jets and outflows that emit strong radio waves. By studying these radio emissions, astronomers can learn about the properties of these active galactic nuclei and their impact on the host galaxies. A cosmic cocktail. Unveiling the composition of celestial objects with radio waves. Every celestial object, from the swirling dust clouds within our galaxy to the colossal galaxies billions of light years away, possesses a unique chemical fingerprint. Radio astronomy plays a crucial role in deciphering this fingerprint, revealing the composition of these objects and the elements that make them up. Spectral lines. When radio waves interact with atoms and molecules, they can be absorbed or emitted at specific frequencies. These unique absorption or emission lines act like a barcode, revealing the presence of specific elements within the object. By analyzing the radio spectrum of an object, astronomers can identify the presence of hydrogen, oxygen, complex organic molecules, and even rare elements, providing insights into the object's composition and the ongoing physical and chemical processes within. Interstellar medium. Radio observations of the interstellar medium allow astronomers to study the abundance of different elements throughout the galaxy. By understanding the distribution of elements like hydrogen, helium, and heavier elements forged within stars, we can trace the chemical evolution of the galaxy and learn about the processes that enrich the interstellar medium with the building blocks for future star and planet formation. Star formation and evolution. Different stages of a star's life cycle are associated with specific radio emissions. By studying the radio spectrum of a star-forming region, astronomers can identify the presence of young, hot stars, massive star-forming clouds, or even the remnants of exploded stars. This information provides a valuable tool for understanding the birth, life, and death of stars within our galaxy and beyond. Pulsars, nature's cosmic clocks and laboratories. Pulsars, rapidly spinning neutron stars, the incredibly dense remnants of massive stars that have undergone supernovae explosions, are some of the most fascinating objects studied in radio astronomy. These celestial objects emit beams of radio waves that sweep across the sky like a cosmic lighthouse, with their rotation periods acting as incredibly precise clocks. Pulsar timing. The regularity of a pulsar's radio pulses allows astronomers to use them as natural clocks in the universe. By meticulously measuring the arrival times of these pulses, astronomers can detect even the slightest variations in the pulsar's rotation period. These variations can be caused by a variety of factors, such as the presence of a companion star or the pulsar's wobble due to its internal structure. Studying these variations provides valuable insights into gravity, the behavior of matter under extreme conditions, and even the existence of unseen companions orbiting the pulsar. Extreme physics laboratories. Pulsars act as natural laboratories for studying the laws of physics under extreme conditions. Their immense gravity and rapid rotation create environments where matter behaves in ways not easily replicated on Earth. By observing pulsars and their interactions with their surroundings, scientists can test theories of gravity, probe the nature of strong nuclear forces, and gain a deeper understanding of the fundamental laws governing the universe. Search for extraterrestrial intelligence, SETI. Radio waves, due to their ability to travel vast distances relatively unaffected by interstellar dust and gas, are a prime candidate for searching for potential messages from extraterrestrial civilizations. Some radio astronomy projects dedicate observation time to scanning the cosmos for narrowband radio signals that might be artificial in origin, with pulsars being a specific target due to their precise periodicity. While no definitive evidence of extraterrestrial intelligence has been found yet, the search continues, and radio astronomy plays a crucial role in this ongoing endeavor. Unveiling the Invisible, Radio Astronomy and the Quest for Exoplanets. The discovery of exoplanets, planets orbiting stars beyond our solar system, has revolutionized our understanding of planetary systems. However, directly imaging these distant worlds is incredibly challenging. Radio astronomy, while not offering direct images, plays a crucial role in the detection and characterization of exoplanets. Transit method. When an exoplanet passes directly between its star and us, it causes a slight dip in the star's brightness as some of the starlight is blocked. By monitoring radio emissions from the star, astronomers can sometimes detect tiny wobbles in the radio signal caused by the gravitational tug of the orbiting planet. This technique, known as the radio transit method, can confirm the presence of exoplanets previously detected by other methods and provide insights into their mass and orbital parameters. Pulsar planets. Pulsars, with their incredibly stable rotation periods, can be used to detect the presence of planets orbiting them. As a pulsar and its planets move through space, the gravitational interaction causes slight variations in the arrival times of the radio pulses. By analyzing these variations, astronomers can detect the presence of planets and even measure their masses. Protoplanetary disks. Before planets form, they reside within swirling disks of gas and dust called protoplanetary disks. These disks emit faint radio waves, which can be studied by radio telescopes. By analyzing the properties of these radio emissions, astronomers can gain insights into the composition and structure of the disk, potentially revealing clues about the ongoing formation of planets and the potential for future planetary systems. The future of radio astronomy. Technological advancements. Radio astronomy is a rapidly evolving field, constantly pushing the boundaries of sensitivity and resolution. New technologies are emerging that promise to revolutionize our understanding of the cosmos through radio waves. Interferometry. This technique combines signals from multiple radio telescopes spread over vast distances, effectively creating a giant virtual telescope with incredible resolution. Interferometry allows astronomers to observe faint objects in greater detail and study the fine structures of celestial objects, such as the environments around black holes or the detailed distribution of gas within galaxies. Next-generation telescopes. Several cutting-edge radio telescopes are under construction or planned for the future. These telescopes, with larger collecting areas and advanced technologies, will be able to detect fainter signals from even greater distances. This will allow astronomers to probe the early universe in unprecedented detail, study the formation of the first stars and galaxies, and potentially reveal new and unexpected phenomena in the cosmos. Multi-wavelength astronomy. Radio astronomy rarely operates in isolation. By combining observations at radio wavelengths with data from optical, infrared, X-ray, and other telescopes, astronomers can create a more holistic picture of celestial objects. This multi-wavelength approach allows for a deeper understanding of the physical processes at play within these objects, revealing a more complete story of the universe's grand narrative. The legacy of radio astronomy. A new window on the cosmos. Radio astronomy, once a young and unconventional field, has become a cornerstone of modern astronomy. By providing a new window on the cosmos, it has revolutionized our understanding of the universe on all scales. From unveiling the invisible wonders within our own galaxy to peering into the depths of the early universe, radio astronomy has transformed our cosmic perspective. Radio waves whisper stories of a universe teeming with activity beyond the limitations of visible light. By carefully listening to these cosmic whispers and meticulously analyzing the radio signals, astronomers have unlocked a treasure trove of knowledge. Radio astronomy continues to push the boundaries of our understanding, challenging existing theories and leading to groundbreaking discoveries that reshape our view of the cosmos. As we continue to listen to the symphony of radio waves, the universe continues to reveal its secrets, one celestial song at a time.